Hello viewers, in this lesson we are going to investigate the idea of domain and range of a function a little more deeply. Getting back to our metaphor of function as a machine, we understood that all the inputs that can be processed by the function machine are called the domain. That is, domain is set of inputs which can be processed by the function machine, whereas the range is the set of outputs. And so, if f is a function from set x to y and ordered pair x comma y belongs to f, then y is f of x and y is image of x under f. X is also called the pre-image of y under f. Keeping in language of what f being a relation as a collection of ordered pair is, we also define domain to be the set of all first elements of the ordered pairs in the function f from set x to set y. That is, domain is collection of all values of x, whereas range is the set of all second elements, that is the image written as most often as y in a relation f from a set x to set y. Now, that being the basic definition, are we ready now to look at more complex functions like this one to find the domain and range of the function? So, this is a special function given as square root of 9 minus x squared. What is the domain and range of the function? That is, what are the values over which this f can act and what are the values that this function f produces? In order to understand this, let us take a quick look at a little visualization and understand exactly what this function looks like and how it behaves. Do you know what the graph of square root of 9 minus x squared looks like? No? Then follow me here. This is how you may get the graph of square root of 9 minus x square if you use any graph software, either an online graph calculator, and here I have used GeoGebra. This root 9 minus x square actually is nothing but the graph of a semicircle lying above the x axis. Now, A is any point on this semicircle, and as I move the point A, you will see a red trace being followed on the x axis. That is nothing but the values of the x, that is the first element present on the ordered pair which is following this relation. So, all x coordinates of the point A are being plotted along the x axis, and you can see that in this case that trace did not go beyond minus 3 and 3 on either sides of the point. So, we are looking at the red trace remains strictly between minus 3 to 3. How does one get that understanding algebraically? That is, without having this visualization or a software just next to us, how do I get the domain of this function? Let us get back to our algebraic work for that. Now, you know very well that square root of a negative number is not a real number, and we are talking about real functions and real valued functions, and therefore, with that condition we begin our working. If f of x is root of 9 minus x squared, then it is only defined when 9 minus x squared is greater than equal to 0, and from there we find the condition on x. As you can see, x square must be less than equal to 9, and that gives us x lying between minus 3 and 3, both the endpoints included. That is how we express our domain. Domain of f is therefore the closed interval minus 3 to 3, and that is exactly what you saw in that visualization earlier. All the values of x were lying enclosed between the interval minus 3 to 3, starting from minus 3 stopping at 3, inclusive of these two endpoints. Now, how about the range? The range of this function can be calculated by starting with y written as root of 9 minus x square. Now, square root of 9 minus x squared is always a positive quantity. Square root function is defined only, that is the outputs of the square root functions are defined to be always the positive values. So, that the function or the in fact the expression, the connection, the correspondence remains a function. There is a unique number mapped to root of 25. So, root of 25 is not plus and a minus 5, but only as per the definition positive 5. With that in mind, the very first condition on y is that y is greater than or equal to 0. At the same time, if I square both these equations, I will get y square is equal to 9 minus x square, getting a condition on y through x. X squared therefore is equal to 9 minus y squared. What does this tell me? 9 minus y squared must be greater than or equal to 0, because x square is such, and therefore y lies between minus 3 and 3. And therefore, if I put number 1 condition and the second condition in mind, the intersection of the solution on y turns out to be y lying between 0 to 3, 0 and 3 included. And therefore, we say that the range of f is a closed interval 0, 3. Going back to the shape of the function, as I said earlier, graphs are the faces of the function. So, if I know that this function represents a semicircle, then you can see that in this picture the y values cannot be less than 0, cannot be more than 3, and that is what the range of the function is, collection of all the outputs values of y put together as a set. And therefore, when you see this blue mark there, that represents all the values of y that every point on the graph can take, and so range of function is a closed interval 0, 3. So, our next question says find the domain and range of the function f where f of x is equal to 1 by 1 plus x square. Now, what you really need to understand is that the domain consists of all the values of x for which f is defined, f can act on them. In this case, the denominator 1 plus x square can never be 0, right, because when x square plus 1 is 0, it would mean x square is equal to negative 1, which is not going to happen because x square is always positive. And that means that f is defined for all real numbers, and that is what the domain of f would be. And so, we say that since f is defined for all real values of x, the domain of f is set of all real numbers. If you look at the graph of this function, you would find it to be a very interesting shape, and all the values of x that can be traced on the x axis corresponding to every point on the graph covers the entire of the x axis, which is what the set of real numbers are. So, we are looking at the domain of f to be the entire of real numbers. How about the range? Now, I am not going to give you an answer right now, but first look at the graph and see if you are able to estimate the values of y. Can y be negative? No. With the shape right there in front of you, you can definitely say that. Also, 1 plus x square is always positive, and therefore, 1 by 1 plus x square will also be positive, and so the outputs will always be positive real numbers. Will they be ever equal to 0? Can 1 by 1 plus x square be equal to 0? No. So, you have a condition inbuilt in the function's definition itself. So, for the range, if I start with f x equal to 1 by 1 plus x square, then one of the things that I can always do is I can write it to be y equal to 1 by 1 plus x square, and from there find what the condition on x in terms of y would be. So, expressing x in terms of y, I have x square is equal to 1 minus y by y. Now, let us apply the logic. x square is always greater than equal to 0 and x is a real number. So, the right hand side, that is 1 minus y by y, must always be a real number and must also be greater than or equal to 0. That means y definitely cannot be 0. That is what we saw by the picture as well earlier. Here therefore, the other condition on y would be, since 1 minus y by y is a quotient of two expressions, and that would either both the functions, that is expression 1 minus y and y, are positive or both are negative. The common solution therefore, if 1 minus y is greater than equal to 0 and y is strictly greater than 0, because y could not be 0 as we saw earlier, then the common solution that arises from here is that y must be less than equal to 1 and y must be greater than 0. The other possibility comes up with y must be greater than equal to 1 and y is less than 0. Now, is that possible? Can you have y greater than equal to 1 and less than 0 simultaneously? No. So, the second possibility is not going to happen, and therefore, the condition on y that we get, that is the range that we are looking for the function f, comes out to be same as the interval which is open at 0, but close at 1. Y is greater than 0, but less than equal to 1. So, if you re-look at the graph of this function, you will understand and appreciate what you have done right now. You have found the values of y which are exactly giving that shape to the curve. The y remains little more than 0, but less than or equal to 1, and that is the significance of the term range of a function. So, both domain and range together decide what the shape of the function is going to be, that is the graph of the function going to be, and vice versa. If you know the graph, you know the domain and range. One more question: find domain and range of the function f where f of x is equal to x plus 1 by 2x plus 3. Now, these are very tricky functions to graph on a graph paper, but we understand that if it is a rational function, it can only be defined when the denominator is not 0, and that is how you begin thinking about the domain. The domain would be for all those values of x for which 2x plus 3 is not equal to 0. That is when x is not equal to minus 3 by 2. And therefore, what is the domain? Domain is all real numbers except the number negative 3 by 2. So, we write it as the difference of real number with the set containing minus 3 by 2. Simple, right? To find the range, very mechanically what you may do is write y equal to x plus 1 by 2x plus 3, cross multiply, collect the terms of x and express x in terms of y. Doing that, you get x is equal to 1 minus 3y by 2y minus 1. Now, apply the same logic as we had earlier. X is a real number other than minus 3 by 2. Therefore, the right hand side must also be a real number. That means, the denominator in the right hand side, which is 2y minus 1, should not be 0. Isn't that so? And therefore, y cannot take value 1 by 2. Other than that, there is no condition on y. So, the range of f turns out to be all real numbers except 1 by 2. So, both domain and range are actually the entire of real numbers except for a particular number. For domain, negative 3 by 2 is never touched on, and for range, half is never attained. So, the output never results in 1 by 2. Does that affect the shape of the graph? Definitely. The graph of this function looks something like this. Maybe you have never tried and plotted such a function earlier. And it is interesting to note that when x is minus 3 by 2, that is, look closely at x is equal to minus 1.5, and you will find that there is no corresponding point or part of the graph at which you will be able to mark a point. Also, since the range did not have half in it, so corresponding to y equal to half, there will be no point on the graph. That means, the graph will not attain the height of half, 1 by 2.5, and that is what is so interesting about functions, domain and their ranges. This concept that we have done today is definitely an abstract concept, but if you sit and try some more functions of the similar kind, you will soon start enjoying it. Let us see if you can do that, and I hope it works for you. Good luck.